Well, hi folks. I promised you that I would stop by and make a little video to go along with the stuff we had just talked about in class last week, because I want you to be able to get the homework all squared away and at least understand what you're trying to do on those problems. So just decided to make a little video. Feel free to pause or rewind any piece of this. If there's things you want to see a little bit slower, you can always do that. I'll try to keep this short and to the point. I'm just going to kind of remind you of the theorem we did last time, and then just basically make a quick definition and state another theorem, and maybe do an example. So, not going to be a lot, just kind of enough to kind of get you to the next step in this section 2.5, which is a really important section. Change of basis, right? So you have two different bases, beta and beta prime. Of course, they're always ordered, and those are two bases for the same vector space V. So the theorem that we mentioned last time in class is that you can write the coordinate vectors for V relative to both beta and beta prime. And the idea is that we would expect them to be related to each other. This theorem relates them to each other, right? So the coordinate vector of V relative to beta is here, and relative to beta prime is over here. And the way you go from one to the other is through this matrix right here, I sub V from beta to beta prime. Okay, so this allows you to take the beta coordinates and rewrite them in terms of beta prime. Of course, we can reverse the whole process and take beta prime coordinates and rewrite them in terms of beta in just the same way. All we have to do is switch the positions of the beta and beta prime in our formula from part A. So really part B and part A of the theorem are the same, with the roles of the beta and beta prime reversed. Very easy to prove. I mentioned this already in class, that basically if you just know the fact that I sub V, right, that's just the identity transformation on V. It just fixes every vector. Knowing that, and knowing theorem 2.14, you can immediately get these results. So it might not be a bad idea to just, for yourself, go back, just make sure that you really do believe that it's just that simple. If there's any questions, of course, you can ask me about it, but hopefully when you take a look at theorem 2.14 and kind of substitute this into the calculation there, these equations become very, very natural. Okay, so just a quick definition here, because this is mentioned in the homework and I didn't actually state this last time. The matrix, which is in the book going to be called Q, and this is just the matrix that is the matrix representation of the identity transformation from beta prime to beta. Remember, we're going from the lower index, or from the lower basis to the upper basis, right? This is called the change of coordinates. So change of coordinates matrix. It makes sense. We're using it to change coordinates, right? Change of coordinates matrix from beta prime to beta. And that makes sense also. It's from beta prime, that's the lower basis, to beta, which is the upper basis. And in the formula, if you look especially at part B, right, you start off with beta prime coordinates for the vector little v, and applying this matrix, which the book is going to call Q, right, gets you the coordinate vector of the same v relative to beta. So this is converting, this matrix allows you to convert your coordinates from beta prime to beta. Okay? Of course we would then not be surprised to see that the inverse of that matrix, we already know the inverse of that matrix, Q inverse, is simply going to be the change of coordinates matrix going the other way from beta to beta prime. Okay? So this formula here, the part A in the formula is really just Q inverse times the coordinate vector of V relative to beta. And the second formula is just, on the right hand side, Q times the coordinate vector of v relative to beta prime. Okay? So, you know, there are times when multiple bases are important to look at, right? So you might have two different bases that you care about. And I'm going to show you some examples of that next week. But for right now, I won't get too much into that. But suffice it to say that being able to convert or change coordinates from one basis to another is important. And this is the matrix Q is your ticket to getting that done, right? So let me point out a couple of other quick little things. Well, actually, let me just do an example of that. Okay, so just as a quick example, suppose that V is P1 of R, right? And let's suppose that beta is the basis 1 and x, and beta prime is the basis 2 plus x and 1 plus 3x. Two different bases for V1. V1 is two-dimensional, and in both cases I've given you two non-proportional vectors. So the vectors in beta are definitely linearly independent, and the vectors in beta prime, likewise, linearly independent. So these are two great bases, okay? So then let me just give you an example of a vector. Let's suppose that V is the vector, I don't know, let's make something up here. How about 5 plus 6x? So that's just some vector in V, okay? And let's suppose we want to find the coordinate vector of V relative to beta prime, right? So, well, it's actually very easy to get the coordinate vector of V relative to beta. So what I'm going to do is I'm going to get this answer by using, I guess this would be the Q inverse matrix, right? The identity transformation from beta to beta prime, and then multiplied by the coordinate vector of V relative to beta. Okay, so I'm going to use this formula because this vector right here, if I want to write V in terms of beta, well, it's just 5 times the first vector plus 6 times the second vector, right? That's pretty simple. Okay, so the trick is going to be to figuring out this matrix right here. This matrix, change of coordinates matrix from beta to beta prime. However, it's actually easier to get the change of coordinates matrix the other way. In other words, if I take the identity transformation and I want to write its matrix from beta prime to beta, that turns out to be much easier because all I have to do is take the beta prime basis, right? Transform it under this transformation. Well, this transformation does nothing to it. This is the identity transformation. So I'm taking 2 plus x, I'm applying the identity transformation to it, I'm getting 2 plus x, and then I'm writing that in terms of beta. Well, the constant was 2, and the coefficient of x was 1. Okay? And similarly for this one, if I transform 1 plus 3x, my second column here is going to be just 1 and 3. So that's easy to get. And because that's so easy to get, I would suggest you just find this matrix first, and then take the inverse of it. Because this matrix, this is the matrix representation, sorry, the change of coordinates matrix from beta to beta prime, which is the inverse of this matrix. So we take the determinant here. I'm just going to use the formula for the inverse of a 2 by 2. 1 over 5. I have to swap the diagonal entries and take minus signs on the other two entries. This is the formula, right? This is how we do this. And I don't have to simplify that, but I'm going to right here. Okay, so this is what we would get if we put the denominators into it. And so now I can come over here and fill that in. 3/5, negative 1/5, negative 1/5, and 2/5. And we would just multiply that by 5/6. Okay? Let's just do that really quick. It looks like on the top we're going to get 3 minus 6 over 5, whatever that is. We'll simplify it in a minute. And on the bottom we're going to get negative 1 plus 12 over 5. Okay, and so if we simplify that, this should come out to 9 over 5 and 7 over 5. Okay, so what does that mean? Well, that means that V, this is the punchline now, V is going to be equal to, these are the beta prime coordinates, so it's going to equal 9/5 of the first basis vector, 2 plus x, plus 7/5 times the second basis vector, which is 1 plus 3x. Okay? We should be able to multiply that out and get our original vector v back again. Right? This should be the same, of course. It's the same vector. These should be equal to each other, and I'm pretty sure that they are. So I'll let you guys double check that. So that's kind of a neat way of calculating the coordinate vector of v relative to a not so nice basis, right? Is to actually first find the change of coordinates matrix from the ugly basis to the nice basis. I'm sorry, from the ugly basis to the nice basis. It's always good to have the nice basis up here on the top. The ugly basis down here. This matrix is usually pretty easy to figure out. As long as that upper basis is a nice one, such as the standard basis beta here, then getting this matrix is pretty simple. And if you really need to have the nice basis on the bottom and the ugly one on the top, like what we need right here, well, then what we can do is just take the inverse of this matrix. Okay? So that's kind of a neat idea. Okay, one last little thing. We've also talked about a matrix representation for a linear transformation. So let me clear some space here. Again, feel free to pause or rewind anything that you're hearing here. But suppose that t, which goes from v to itself, is linear. Let's suppose it's from v to itself here. Okay, so the question that you might wonder is, how are the matrix representation of t from a basis beta to itself, in other words, the same basis on the top and the bottom, how are that matrix and, let's say, another matrix representation using a different basis, how are those related? Okay, so this is actually kind of a cool thing. It turns out that if we just go back and remember, so remember we had the matrix Q. Q was the matrix that is the identity transformation of V, going from beta prime to beta. And of course Q inverse was the identity transformation of V, going from beta to beta prime. We have these two matrices here. Well, it turns out that if you take, so just take a quick look at this, if you take Q, which is the one on the top here, and to the right of that you put your matrix representation of t from beta to itself, take a look at what happens. Okay, so the Q, that's just I sub v, beta prime to beta, and then times t from beta to itself. That actually does not work, and that's because I've done the wrong one here. Sorry, I want to do, sorry, let me start over. Let me start over. I wrote down the wrong thing. I want to start with Q, and I want to multiply it by the matrix representation of t relative to beta prime. That's what I meant to do. Because this upper basis has to match the lower basis on Q for it to make sense, right? We're going to be multiplying these matrix representations here. So I sub v from beta prime to beta, and then times t from beta prime to itself. Okay, well, we can put the I sub v times t together, right? This is using the theorem 2.11. Theorem 2.11 allows you to do that. And now this is just T composed with the identity transformation. Well, that's just T. Or if we want, we can actually just start with the identity transformation and then compose with T. So you'll just get this result here. And now I can use Theorem 2.11 again and split it apart again. Okay, so I'm going to have I sub V from, that's going to go from beta prime to beta, and then T from beta to beta. This matrix here is just Q as well. So we get T. Notice that we are getting the Q now on the opposite side from where it started. Okay. The punchline of that is this theorem. These matrices, these two matrices are very related. And here is how they are related. The matrix representation of T from beta prime to itself, that's this matrix here. I can left multiply by Q inverse in this calculation that I just did. And I'm going to be expressing on the right side of the equation, I'm going to have the matrix representation of T relative from beta to itself. This is the theorem, okay? This is the theorem. And so these matrices are very related. For example, if you take the determinant of this expression on the right side, the determinant of the Q and the Q inverse, they cancel, right? We learned that when we learn about determinants. So you just get the determinant of T relative to beta, and that's supposedly equal to the determinant of T relative to beta prime. Okay? So two different matrix representations relative to two different bases are very related. They both have the same determinant, which means if one of them's invertible, then so is the other one, right? A whole bunch of other things that we're going to get into as well. But this is a nice theorem. The proof of it is just this calculation that's right here. So anyway, that should help you with some of the homework that you're going to be doing for this coming week. I just wanted to give you a head start on the material. I didn't quite get done with this last time. I'm going to do examples of this as we come back together in the coming week, so don't feel like you have to have this totally mastered yet, but I'd at least like you to see it and be able to use it to start thinking about the problems, okay? Hope that makes sense. Hope you're having a good weekend and enjoying the linear algebra. I'll see you guys again very soon. Thanks a lot.